So now we are moving on to graphing rational functions. Before we can graph a rational function, let's just do a quick review of what a rational function even is. A rational function is a function that is the ratio of two polynomial functions. So if we have f of x equals n of x divided by d of x, where d of x does not equal 0, that's an example of a rational function. I bet you can guess why I chose n of x and d of x. So we need to learn all of the steps for graphing rational functions. And yes, I say all because there are a lot. The first step is to always find the x-intercepts. To do this, we are going to factor the numerator and set it equal to 0. This will give us the x-intercepts, or roots, or zeros of our rational function. Next, we need to find vertical asymptotes. To find these, we factor the denominator and set that equal to 0. Vertical asymptotes are dashed lines that the graph will never cross. That is because you and I both know that we cannot divide by 0. Therefore, we can never input a factor of the denominator into our function, or else it would not be defined. The next step is to find holes if they exist. They will not exist on every rational graph, so that is why the if they exist clause is thrown in here. Basically, if both the numerator and denominator have a common factor, let's say x minus c, then the function will have a hole when x equals c. Because these are not on every graph of a rational function, let's go ahead and look at a little example quickly, just because it's not going to come up on the example that we are doing after these notes. Looking at this example of x squared plus 3x plus 2 over x plus 2 as our function, we can see that the numerator factors to x plus 1 times x plus 2. The denominator can stay as x plus 2. But notice, what's going to happen is the numerator and denominator both have a common factor of x plus 2, so they'll technically cancel out. This technically means that f of x will simplify to just x plus 1, which is a linear function. You know what that graph looks like. It should be a linear function with a slope of 1 and a y-intercept of 1. Remember, y equals mx plus b. However, negative 2 is not in the domain of this graph. That means when the line passes through x equals negative 2, we're going to actually have a hole there. This is definitely more of a sketch, but you can see that we have our linear function, straight line, slope of 1, y-intercept of 1, but when x equals negative 2, I have an open circle. That's what a hole looks like. Let's continue on with the rest of the steps for graphing rational functions. The fourth step is definitely the one with the most information. We need to find the horizontal or oblique asymptote and then determine if the graph crosses it. In order to find the horizontal or oblique asymptote, we need to expand both the numerator and denominator if they aren't already. Then we look at the degree of each. We're going to let n equal the degree of the numerator and m equal the degree of the denominator. No, I did not choose these letters. These are the letters that your book uses. There are 4 potential things that can happen. First of all, if the degree of the numerator is less than the degree of the denominator, a horizontal asymptote of y equals 0 will exist. If the degrees equal one another, a horizontal asymptote will exist, but you need to divide the 2 leading coefficients to find it. If the degree of the numerator is exactly 1 larger than the degree of the denominator, an oblique asymptote will exist. You can do long division to find it. Only the quotient matters, so don't worry about the remainder. And lastly, if the degree of the numerator is more than 1 larger than the degree of the denominator, no horizontal or oblique asymptote will exist. Notice, one of these 4 things has to happen, so make sure you know which one and do the appropriate steps to finding the correct asymptote if it exists. Step 5 is to create your interval chart. Be sure to include all critical points on this interval chart. That's anything that makes the numerator or denominator 0. In other words, the x-intercepts from step 1 and the vertical asymptotes from step 2. Finally, you can put everything together to sketch your final graph. Make sure to always label those important points and include at least 3 points and asymptotes all labeled before you turn it in. Now, I know this is a lot of information, so let's go ahead and look at an example. We're going to look at this problem as our example. I did leave our 6 steps up here just so we can follow along. So we're going to go ahead and look at graphing x squared divided by x squared minus x minus 2. For the first step, we need to find the x-intercepts. Remember, in order to do this, we need to factor the numerator and set it equal to 0. This should be a pretty easy one. Go ahead, see if you can figure out what the x-intercept is. Hopefully you determined that because the numerator was equal to x squared, x equals 0 is the x-intercept. Remember, as you find each step, you can go ahead and put it on our graph. Be sure to label if necessary. Step 2, we need to find the vertical asymptotes. In order to do this, we need to factor the denominator and set it equal to 0. Take a second, pause the video, factor the denominator, and see if you can determine where the 2 vertical asymptotes are. Hopefully you found that the denominator factored to x plus 1 times x minus 2. Using the zero product property, this means that x equals negative 1 and x equals 2 are the vertical asymptotes. Remember, these vertical asymptotes are dashed lines that the graph will never cross. In fact, they're vertical lines because they're vertical asymptotes. Go ahead, put them on your graph. Be sure to label them with the correct equations. Go ahead and check your graph. Be sure that it looks like mine so far. If it does, great job. If not, be sure to pause the video and go back and figure out where you went wrong. Now we can move on to step number 3. Find the holes if they exist. Well, in the numerator, we had an x squared. The denominator, we had factors of x plus 1 and x minus 2. Even if you were to write the numerator as x times x, there's not going to be any common factors between the numerator and the denominator, so there's not going to be any holes. Awesome job. We're already on to step 4. Remember, this is the complicated one, so we need to go ahead and look at just the degree of the numerator and the degree of the denominator. Well, our numerator has a degree 2. Our denominator also has a degree 2. Therefore, this matches the second criteria here for finding horizontal or oblique asymptotes, where the degrees match one another. It says a horizontal asymptote is going to exist. We need to divide the 2 leading coefficients to find it. So let's go ahead and do that. If we divide the 2 leading terms and or leading coefficients, you can see that we have 1x squared over 1x squared, which is just 1. This means that y equals 1 is the horizontal asymptote. This too will look like a dashed line, although in this case a horizontal line. So let's go ahead and draw it in. When drawing it in, be sure that you are labeling it with the appropriate equation, just like you did the vertical asymptotes. Now remember, there's a second step to step number 4. We need to determine if the graph crosses it. That's right, I said that the graph can actually cross a horizontal asymptote. It could also cross an oblique asymptote if that's what we had, but in this case, we have the horizontal asymptote, so that's what we need to test. Only vertical asymptotes are the lines that graphs will never cross. We can use algebra to figure out if it crosses a horizontal or oblique asymptote. In order to do this, take the original function, in this case, the x squared over x squared minus x minus 2, and set it equal to the equation of the horizontal asymptote. So in this case, 1. If you set these two equations equal to one another, you should be able to now use algebra to solve. The first thing I'd recommend doing is multiplying both sides by that denominator. If you do this, you should get that x squared equals x squared minus x minus 2. Go ahead, keep solving for x. See if you can figure out what x will equal. If you solved correctly, you should get that x equals negative 2. What does this mean? This means that at x equals negative 2 on our graph, the graph will cross the horizontal asymptote. That is the only time, though, that it should cross this asymptote. I'm going to go ahead and put a dot there so that I don't forget. Can you believe it? We are already on to step 5. Step 5 is to create our interval chart. We need to be sure we're including all critical points. So we have x equals 0, x equals negative 1, and x equals positive 2. Go ahead, make your number line for your interval chart and put those 3 critical points in the correct order on there. Now, remember for your interval chart, you need to choose an x-coordinate in between each value of these critical points. I'm going to choose x equals negative 2, x equals negative 1/2, x equals 1, and x equals 3. You know what to do next. Pause the video and take time to actually plug in each of these x values to your function and see what you get out. Hopefully these are the y values that you got. When you plugged in x equals negative 2, you should have got out y equals 1. X equals negative 1/2 should have led to y equals negative 1/5. X equals 1 should lead to y equals negative 1/2. And lastly, when you plugged in x equals 3, you should have gotten y equals 9/4. What does this tell us? 1, it tells us 4 points from the graph, but it also tells us the behavior of the graph in relation to the x-axis. Again, remember, we only had one x-intercept, so we can't cross the x-axis more than the single point when x equals 0. Because y is positive 1 when x equals negative 2, that means everywhere to the left of negative 2, it's going to be a positive value, which means we're going to be above the x-axis. Between negative 1 and 0, the y-coordinate was negative. Because it's negative, that means we're going to stay below the x-axis. Between 0 and 2, y was also negative. Therefore, we will be below the x-axis. And then lastly, to the right of 2, the y value was positive, which means we will be above the x-axis. I'm going to go ahead and put these points first on the graph, and then we'll talk about the curve of the graph. There's my 4 points. Be sure to label them. Unfortunately, I can't zoom in on this video, so I'm not going to try to label with the fractions and stuff, but please label the coordinates. For example, if you go to this point right here, I can't tell what that is without a label, so you want to make sure you're labeling it as negative 1/2, negative 1/5. This one, you'd want to label as 1, comma, negative 1/2, and so on. If you write your numbers really largely and you can't fit it on the grid, that's okay. Go ahead and label them with numbers or letters, and then off to the side you can write the coordinate points. That's totally fine. It also helps keep your graph a little bit neater. So the final step, step 6, is to then sketch the graph. Now, this may look kind of interesting and a little intimidating almost because we only have 5 points and 3 asymptotes. But rational functions will always try to get as close to asymptotes as they can. So, what's going to happen on let's look at the middle section first. We have the x-intercept and then we have those 2 points. Ultimately, it's going to try to get really, really close to the asymptotes, and we know that it has to go down because it can't cross the x-axis again besides that x equals 0 point. So if I want to go ahead and sketch my graph, I would basically go down like this and like this. Let's go over to the right section, so to the right of x equals 2. We have that 1 point, 3, 9/4. But again, it's going to try to get really, really close to the asymptotes. So it's going to look something like this. Notice, it's not going to cross the asymptotes. It's just going to get really close. Now, to the left of x equals -1 gets a little bit tricky. Going up towards the vertical asymptote like this isn't too bad. But the most common error that students will do is they'll cross that vertical asymptote and they'll continue their line down and cross the x-axis. That doesn't work because we do not have another x-intercept. Rather, when we cross that horizontal asymptote, we need to make sure that we're still trying to get really, really close to it. So it actually bends back up and tries to touch the asymptote. This is what your final graph should look like. We'll continue doing more examples together in class this week.